Let's talk about the chemistry of aldehydes and ketones, or carbonyl compounds in general. First, we'll talk about how to prepare them. One way of preparing them is by taking an alkyne and reacting it with Hg2 plus mercuric ions with dilute sulfuric acid and 60 degrees Celsius, in which it will form the respective uh, aldehyde or ketone. Here is a reaction that we called Friedel-Crafts acylation, in which we take alkyl halide with a Lewis acid catalyst like anhydrous aluminum chloride, and we react it with benzene. The hydrogen of benzene will go away with the chlorine as hydrochloric acid, while the rest join to form a respective uh, carbonyl compound with an aromatic ring attached to it. This is benzaldehyde, and there's an easy way. We can't use uh, like uh, formic chloride to because such a compound doesn't exist where the R group is a HC double bond O Cl. That compound doesn't exist. So we had to use this thing called Gattermann reaction if we want to get benzaldehyde from benzene, which is basically carbon monoxide, concentrated hydrochloric acid, and anhydrous aluminum chloride. Here, another way of obtaining carbonyl compounds is by oxidizing alcohols. Here, if we were to oxidize a primary alcohol with a weak oxidizing agent like anhydrous pyridinium chlorochromate, we will obtain an aldehyde. If we were to take a strong oxidizing agent like H plus MnO4-, it will oxidize to the respective carboxylic acid. It will further oxidize to form ethanoic acid in this case. But if we were to take a secondary alcohol, it cannot oxidize into a carboxylic acid. So even with a strong oxidizing agent, it will oxidize to form a ketone. Now for the reactions of carbonyl compounds. This is a reaction known as Aldol condensation, which we will discuss further under organic mechanisms. But for now, just note that that carbonyl compounds, they can react with bases to form this compound called the aldol, as we can see here. Only carbonyl compounds which has alpha hydrogens will be able to do so, okay, to undergo this reaction. This is another reaction we can do to carbonyl compounds. Here we have an aldehyde, and we can do this to ketones also. If we were to add NaCN, sodium cyanide, and dilute and hydrochloric acid, basically HCN, hydrogen cyanide. Basically it's hydrogen cyanide, but we add this because to form this, what we observe is the formation of this thing called a cyanohydrin, in which this double bond O group becomes a hydroxide group, and a cyanide is also added into the carbonyl compound as follows. So this group becomes a hydroxide group, and a cyanide is also added. Another reaction that can be undergone by carbonyl compounds is this Grignard reagent process. We can add an alkyl group to this carbon and convert this double bond oxygen into a hydroxide group with this mechanism by adding RMGC, a Grignard reagent, and dry ether as the first step, and we hydrolyze it with acidic water, and to obtain this. Yeah, we have discussed this before. Another thing we can do is by taking the sodium salt of a terminal alkyne and acetylide ion and reacting it with an aldehyde or ketone, in which case we get this compound where this R group CH3C double triple bond C will attach to the carbonyl carbon, and the Na plus binds to oxygen as O minus Na plus. And if you were to hydrolyze it with acidic water, this group will convert into a hydroxide group to form a resultant alkynol. Another thing we can do is taking an amine and reacting it with a carbonyl compound. Here we took a ketone, and as we see, the O over here goes away with these two H's as water over here, and this double bond will attach to nitrogen to form this compound, as we can see over here. Here we have something called Brady's reagent, 2,4-dinitrophenylhydrazine, in which if we were to add this to a carbonyl compound like an aldehyde or ketone, a red-orange color precipitate forms, which is this compound over here. This is a test for aldehydes and ketones, by the way. This is something called Clementine reduction. Okay, this is Clementine reduction. This thing over here is not Clementine reduction. Okay, it's very confusing because it has also mercuric ions over here, but no, this is not. Please do note that this is not, and it is in fact this, that is Clementine reduction. If we were to add zinc amalgam conc HCl into a carbonyl compound, it will become its respective alkane. We can add deuterium instead of hydrogen by using concentrated deuterium chloride. Another thing we can do is reduce carbonyl compounds into alcohols using reducing agents like lithium aluminum hydride, dry ether, and water. We can oxidize aldehydes into carboxylic acids, and it will thus decolorize the oxidizing agent. Aldehydes can also react with Tollens and Fehling's reagent to form but the precipitates formed will be different to that of terminal alkynes. If we were to put Tollens reagent to a terminal alkyne, a white color precipitate forms. But here, the aldehyde is oxidized into a carboxylic acid, and silver itself is precipitated. This is called the silver mirror test. And if we were to add Fehling's reagent, we will get this sodium salt of carboxylic acid, and we will get cupric oxide, a brick red precipitate. By the way, Tollens could be used to, if we have a compound with both an aldehyde and a ketone group, we can, this is a neat thing that I have noticed, is we can use it to oxidize the aldehyde group into carboxylic acids, but while keeping the ketone, or basically any other, sorry, if we were to have a hydroxyl group and a aldehyde group in the same compound, like say that both of them can be oxidized into higher oxidation states. However, if we were to add Tollens reagent, it will only oxidize the aldehyde group, while the hydroxyl group will not be oxidized at all, which is quite a neat thing. It's something I had to learn by something I noticed while doing conversions. Well, here's a neat thing. The Tollens reagent can also react with benzoic acids to also precipitate silver. So it's not exactly a unique test for aldehydes per se. However, and these are the reactions of aldehydes and ketones.